My name is Gabriel, and before I actually get into the talk today, I just want to tell you a bit about my background. So I'm a life science student, not a math specialist. I am a math minor, and I'm fulfilling that math minor using the specialist courses. So I have somewhat of a background in this proofy math stuff. So I'm basically going to be giving an introductory presentation on what Steiner systems are, and I'll give you some insight into their properties. And then at the end, I'll basically hint at some of the applications of Steiner systems. Okay, so to start, let's motivate the idea of Steiner systems. So imagine that I wanted to send you a message, either a no or a yes, so like a yes-no message. And one way I could do this is by sending either a 0 or a 1, where 0 means no and 1 means yes. Now, if I transmit this message to you and you receive a 0, that probably means I meant to say no. However, during data transmission, there can be things called bit flips, where a 0 can turn into a 1, or a 1 can turn into a 0, and this happens simply due to noise during the transmission process. So if all you're receiving is a 0 or a 1, then it's impossible to tell whether a bit flip occurred during the transmission. So let's make things a bit more complicated. How about I send you 2 digits, either a 00 to indicate no, or a 11 to indicate yes. So let's basically draw this out here. So 00 is what will assign the meaning of no to it, and 11 will be yes. So when I send this message, it's possible for you to receive a 00 or a 11, but due to bit flips, it's also possible to receive a 01 or a 10. Now, because I'm only ever sending you 00s or 11s, that means if you receive one of these messages, you know for sure that an error in transmission has occurred. The trouble is you can't really tell what my original message was intended to be. The reason is that each of these messages are a distance 1 away from any of the, we'll call these valid code words. So 00 and 11 are the valid code words. So that means this code is error detecting, but it can't fix the error, so it's not error correcting. However, what if we spice things up a bit more? What if, let's say, I send you 3 digits, where 000 indicates no, and 111 indicates yes. So now the set of possible messages that you receive, you could have a single 1, in which case the possibilities are 001, 010, and 100, but it's also possible to receive messages like 011 or 101 or 110. So the thing is, if you received a 001, it is possible to tell what my intended message was, because it's much more likely for just 1 bit flip to occur as opposed to 2, right? So basically, one way we can think about this is if the message you receive has 2 zeros in it, then the remaining digit should also be a 0. Similarly, if the message you receive has a 1 0 in it, if the message you receive has 2 1s in it, then the remaining digit should also be a 1. So all of these invalid code words have some amount of overlap. Like, they both contain 0 and 1s. The difference is how many they contain. And so we're basically going to try to build on this idea of constructing sets that overlap somewhat, but not completely. Okay, so we want to build sets that do not overlap too much. And so this basically brings us to the concept of a Steiner system. So before giving the actual definition, let's first work through a construction of this. So let's consider the following numbers. So we'll have t equals 2, k equals 3, and n equals 7. Okay, so this n is going to tell us that we're working with a set, let's call it omega, and this set is going to have 7 elements in it. Now, these elements are arbitrary, they could be anything, so for simplicity, we'll just make this be the integers from 1 to 7. Okay, so we have 1, 2, 3, 4, 5, 6, 7. Sorry, that's lower than expected. Okay, so n equals 7 means we're working with a set of 7 elements. Now, k equals 3 means that we're going to consider subsets of omega with size 3. Okay, so for instance, the numbers 1, 2, 3 could be something under consideration. The key part of a Steiner system is this number here. So for t equals 2, we basically want for any 2 numbers that we choose from omega, we want these 2 numbers to be contained in exactly one set of size 3. Now these sets of size 3, we're going to call them blocks. Okay, so for any 2 elements in omega, we want them to be contained in a unique block. So basically, in this combination of digits, t equals 2, k equals 3, n equals 7, is this possible? Let's give it a shot. So let's start by trying to construct our first block. Let's just start with the numbers 1 and 2. Okay, so I consider the numbers 1 and 2, and I want these to be contained in a unique block. Each block must have size 3, and so why not, we'll just have a block that's 1, 2, 3. So since this is our block, we know that the pair 1 and 3 is also contained in here, and so we don't need to worry about that. Now, what about the pair 1, 4? Well, so far 1, 4 isn't contained in the block yet, so let's give it 1. So this is going to be our second block. And each block, again, because it must have 3 elements, the third element cannot be 2, because if it was 2, then the numbers 1 and 2 would be contained in more than one block. By similar reasoning, it can't be 3. And so let's just, hypothetically, let's make it 5. So now if we consider the pair 1, 5, it's also contained in a block, so we're good on that part. If we consider the pair 1, 6, by similar reasoning to before, we are basically forced to have the number 7 here in our remaining block. Okay, so this takes care of all pairs of numbers with 1 as one of the digits. So now what about other pairs? Now the numbers 2 and 3 is already contained in B1, so we don't really care. What about 2 and 4? So the third element in B4 can't be 5, because otherwise the digits 4 and 5 are contained in more than one block. And so let's just make it 6. If we have B5, let's consider the pair 2 and 5. By the reasoning we've been basically repeating over and over again, we have to have 7 in here. For B6, if we consider the pair 3, 4, the third element in here can't be 5, because remember 4 and 5 is already contained in a block, so we can't have it be contained in another one. And it can't be 4, 6 either, because 4 and 6 is already here, so it's got to be 7. And now, do we still need more blocks? Well, so far the pair of numbers 3 and 5 aren't included in any block, so we'll build one for that. And if you basically just look at what we've built so far, you'll see that we basically have to have 6 in here. So what we have here, and this is the entire Steiner system in this case, where if I gave you any two elements in omega, you can find exactly one block that contains those two elements. And that's the key, like there's exactly one. And so this brings us to the definition of a Steiner system. So a Steiner system, we denote it STKN, okay, is it's a set omega of size n and a collection of blocks I'll use this like curly B thing. A collection, a collection of the curly B should be here, of blocks B, where the size of each of these blocks is K, with the property that for any subset of omega, where this subset has size T, there exists a unique block in our collection such that this block, this subset of size T is contained in this block. Okay, so that's what a Steiner system is. Perfect. Now we do have some requirements on what T, K, and N can be. So we require T to be strictly less than K, which is itself strictly less than N. So you might wonder, why do we not allow equality? Well, we could think about what happens if we do have equality. So suppose T equals K. That means each of our blocks have size K, but for any K elements that we choose from omega, it has to be contained in exactly one block. The Steiner system becomes kind of trivial. It's just the set of all subsets of size K from omega. Meanwhile, if K equals N, well, that means each of our blocks has size N, but omega has size N, so we can only ever get one subset. And so our Steiner system is just a single block, which is omega itself, and that's arguably more boring than the case where T equals K. Okay, so to keep things interesting, we have this strict inequality requirement. So a question that you might be wondering is, well, do Steiner systems always exist? So we built a valid Steiner system for, we built S237, but it might not be a complete surprise that Steiner systems don't always exist. Let's try to construct S123. So because n is 3, that means omega has 3 elements. And we want the property where for any single element we choose from omega, it is contained in a block of size 2, and that block has to be unique. Well, if we picked, let's say, the number 1, and that means the block has to have size 2, so let's say the block is 1 and 2. Then let's take the number 3 from omega. Because this block has to have size 2, the other element has to be either 1 or 2. But if it's 1, that means the number 1 is contained in more than one block. That's invalid. Same thing for if it's 2. And so we conclude that S123 does not exist. Okay? So if Steiner systems don't always exist, then are there any interesting theorems that might give us some insight into whether they exist or not? And so I'll basically show you some theorems concerning the existence of Steiner systems. So first, theorem 1. If STKN exists, then ST minus 1 k minus 1, n minus 1 also exists. Okay, so what's the proof of this? Well, first let's fix an element in omega. Okay, so I'll just outline a proof here. So fix x in omega. And now let's keep all of the blocks from STKN that contain x. Okay, so keep all blocks of STKN that contain x. Okay, now let's think about what this collection of blocks is. Like what property does it have? Well, within this set of blocks, we have that for any t elements we choose from omega, one of which is x, these t elements are contained in exactly one block. Okay. But now let's delete x from omega and the blocks above. Okay, so now what do we have? Well, now we have that every t minus 1 elements of omega, and omega does not have x anymore. So any t minus 1 elements from omega is contained in exactly one of these blocks. Each of these blocks has size k minus 1 because we deleted x from it. Okay. So what we have here is st minus 1, k minus 1, n minus 1, and so this completes the proof. This Steiner system exists. Okay. So my writing is bigger than I thought. So what is the utility of this theorem? Well, for instance, we could consider the contrapositive of this, where if st minus 1, k minus 1, n minus 1 does not exist, then we know that stkn does not exist. So using this theorem, it's fairly easy to see that, for example, S1000, 1001, 1002 does not exist because we showed that S123 does not exist. And if you apply the contrapositive of theorem 1, like 999 times, we get our result. Okay? Alternatively, if you want to prove some Steiner system does exist, one way you could do it is to try and consider a larger Steiner system, and then using theorem 1, you could try to break it back down into what you were trying to prove. Okay, so now for another theorem. So theorem 2. If STKN exists, then k choose t divides n choose t. Okay, so how do we show this? Well, first let's consider the set of all subsets of size t that we can get from a single block. Okay? This sort of by definition is k choose t. So now let B, I'll just write it here, so let B be the number of blocks. Okay? So that means if we consider the set of all subsets of size t that we can get from any single one of our blocks, that is going to be B times k choose t. Now, because we're working within a Steiner system, we know that any t elements that we choose from omega are contained in a unique block. Each block is itself a subset of omega, and so therefore subsets of a block are subsets of omega. And therefore, what we see is that B times k choose t is actually equal to n choose t. So therefore, if we take n choose t divided by k choose t, we get b. So, and b is an integer because it's literally the number of blocks, and that concludes the proof of this. Okay, details squared. Okay, so we have these two theorems. Theorem 2, it's useful because if you can show that you have some combination of tkn where k choose t does not divide n choose t, then you automatically know that this Steiner system does not exist, and so just don't bother checking for it. Okay? Now, we can actually combine theorems 1 and 2 to get something I find quite interesting, where basically if you iteratively apply theorems 1 and 2, you can actually conclude that if tkn exists, then k minus I choose t minus I divides n minus I choose t minus I for I equals 1 up to t minus 1. Right? Okay. So these theorems they can be pretty helpful, especially for proving that certain Steiner systems don't exist. What about if we're trying to show that a certain Steiner system does exist? So this is a result. I want to keep this. So I'm going to present this result without proof. I'm sorry. There's other things I want to talk about. So basically, this theorem, it actually has a name. So it's called Kirkman's existence theorem. Okay? And what this says is S23n exists if and only if n is congruent to 1 mod 6 or n is congruent to 3 mod 6. Okay? Now, I did write up fairly detailed notes for what I'm talking about today. In those notes, I have a link to the proof, so if you're interested, feel free to read this. Just something I want to point out is we built S237 here. 7 is congruent to 1 mod 6. So by this theorem, we know it exists, and certainly it does exist, we built it. Okay? So that is all I'll say about the existence of Steiner systems. So now let's talk about the uniqueness of Steiner systems. So as I was building S237, I made quite a few arbitrary choices. For instance, in block 1, I just said, okay, let the third element be 3. When I was building B2, I was like, okay, let the third element be 5. This 3, when we were first building it, so you can ignore everything to the right of it, this number could have been quite literally any of the others. So you might be wondering, are Steiner systems unique? Well, let's see. So I can basically build another set of blocks. So we have this. And basically another Steiner system we could have is as follows. So I'll just draw it out here. So we could also have 2, 3, 7, 2, 4, 2, 4, 5, 3, 4, 3, 4, 6, I believe, and 5, 6, 7. So if you take a look at all of these blocks here, you'll see that if I give you any 2 numbers, then it again is contained in exactly one of these blocks. So the literal elements that these two versions of S237 that I've drawn here, the elements themselves are different. Like block 1, this one contains 1, 2, 6. Block 1 here contains 1, 2, 3. However, there is a notion of these two Steiner systems being like the same, where remember that the elements of omega are arbitrary. So we could just relabel the elements. So what if there's a way to basically relabel these numbers so that once you rearrange it with the new labels, it looks exactly like this? So if that is the case, then we would call these two Steiner systems isomorphic. And let's first take a moment to think about what such relabeling would do to our tables. Firstly, the order of blocks that we write is completely arbitrary. I could have like swapped these two, for instance, B1 prime and B2 prime, and it would still be a valid Steiner system. So that means I'm free to permute these columns however I like. Additionally, the relabeling of elements, like the relabeling of these numbers themselves, is essentially just a permutation of the numbers 1 through 7. And what this permutation would do is essentially swap around the rows, right? So what this means is that if two Steiner systems are isomorphic, then if you have like these tabular representations of them, they are isomorphic if and only if you can swap around the columns and rows such that it looks like this. Okay? So it's way too tedious to draw out each step of the permutation on the board, but hopefully you can see some similarities that would suggest that such permutations are indeed possible. Firstly, if you look at these numbers, like where these 6s are located, we have 6 in block B1 prime and 2 more 6s in B6 and B7 prime, whereas these 3s are in B1, B6, and B7. Okay, so if you like moved this row so that it became the third row of this table, then that's one step closer towards making this table look like that table. And if you want, as an exercise to the audience, you could basically, right? Yeah, classic. So you can like do the rearrangement and see that this does indeed, you can actually do it. Okay, so Steiner systems can be isomorphic. Do they always have to be isomorphic? If I gave you two tabular representations of a Steiner system, can you always find permutations of the columns and rows such that they become the same? So the only example I know of where it's not the case is S2313. Now, by Kirkman's existence theorem, S2313 does exist because n is 13, but n is congruent to 1 mod 6, right? I'm going to refer you to my notes for more detailed discussion on that. Okay, so basically Steiner systems can be isomorphic, but they don't have to be. Now, one of the major properties of the Steiner system is the fact that for any subset of size t, it's contained in a unique block. So is there a way we can like draw out a Steiner system such that it becomes very easy to identify what the blocks are? If I gave you the numbers 1 and 2, can you identify what the remaining number should be? So there is a nice representation of S237 specifically, and I will draw it out for you here. So it's called the Fano plane. And what it is it's kind of like, think of a circle inscribed in an equilateral triangle. That's literally how it's arranged. So we could put something in here. We could also put elements here. Like that, okay? So we have 7 circles, and the edges are connected by equilateral triangle. The middle one is connected to every single other one, and these 3 circles in the midpoints of each line, they're connected by a circle. So let's basically try to reorganize S237 onto this Fano plane. Because if we're trying to identify blocks for arbitrary Steiner systems, these Steiner systems can get fairly large. S237 is manageable. The table's not too big. If I told you what is the block that contains 2 and 5, it might take a bit of time, but it's not it's not too hard to see that it's 7. Okay, so let's basically put this on here. So I could have the number 1 here. Again, I'm making arbitrary choices. Let's put 1 here, and let's put 2 in the center. Now, because the Steiner system requires that these 2 numbers be contained in a unique block of size 3, this element is fixed. So here we have that it's 3, so I literally have to put 3 here. If I choose some other number, let's say 4, for instance, let's put 4 here. What is the block that contains 4 and 2? Well, if we take a look here, 4 and 2, it contains 6. So we can put 6 here. No, that's not right. We also have 4 and 3 over here. What is the block that contains 4 and 3? 7. Okay, so I was right. 7. And what is the block that contains 2 and 7? The answer is, where's 2 and 7? Here, B5. So it contains 5. Okay? Now, the magic of the Fano plane is that if I gave you any 2 numbers, those 2 numbers will either form a line on this plane or a circle. So, for instance, if I gave you the numbers 4 and 5, what is the block that contains 4 and 5? It is 4, 5, and 1. If I gave you the numbers 3 and 2, what is the block that contains those 2 numbers? It's 3, 2, 1. If I gave you the numbers 5 and 6, well, these, there, it's fixed. Okay, 5 and 6. These guys do not form a line, but they do form a circle. If I trace this circle, I can identify the remaining element, which is 3. Okay, so this Fano plane lets you fairly efficiently identify the missing element, or not really missing, but the remaining element in a block for S237. Okay, so now earlier we talked about the uniqueness of Steiner systems, where I basically mentioned that, you could have isomorphism, but you don't really have to. How many ways can I rearrange this plane so that the blocks themselves are preserved? For instance, if I put these numbers around differently, and I asked what is the block that contains 1 and 2, which should be 3, I want to arrive at the answer 3 for both of the Fano planes. So how many ways can we do that? So when I started the construction, I could have put any of these 7 elements from omega. So I start off with 7 choices. And for the next element, I have 6 choices, right? Because one of them is already taken. The thing is, as soon as I put down 2 elements, there is a third that's already fixed by property of S237. So that means the next element I put, I have 4 choices, because 3 of the 7 are already taken. as soon as I put down that fourth element, everything else is fixed. To try to help convince you of that, suppose I had this middle part filled out. Well, actually, if we just like recall how I constructed it, I first started by filling out this middle part, and then I placed another element just arbitrarily. As soon as I did that, well, because these two are already there, this is fixed. Because these two were already here, this is fixed. And now, because, well, there's different ways. You could think, no, that one's missing. So because these two are there, then this is already fixed. So as soon as you put down that fourth element on the Fano plane, you have no more free choices. Yes?
So you were saying about the Fano plane, they always form like a line or circle. Is that true in general? It's only true.
So this is special for S237.
Oh, like in general, you don't have.
So there is a different representation of like other Steiner systems, but for S237, this is what we have. Okay.
And at least for any finite fields, its projective plane will be more or less the same picture. It's just for the field of two elements.
I'm unfamiliar with projective planes.
This is a projective plane. It's like you can connect any 2 points with a line. And it's a line intersect.
That's okay. But yeah, the main point is we have 7 times 6 times 4, which is something solution exists. So that is how many. That's how many block preserving permutations we have of this Fano plane. So something that I'll just briefly mention is that for the Steiner system S5824, we have what's called the MOG as the representation for this. So in this case, MOG stands for the Miracle Octad Generator. Okay. It's quite the visualization. I will refer you to my notes to read about it. Okay, and now basically for the last portion of today's talk, I just want to mention briefly some of the applications that we have of Steiner systems. And so one of them, we actually don't really need this anymore. Okay, so one of the applications is in what's called coding theory. Okay, so within coding theory, there's a type of code called the extended binary Golay code. So this code has each of its code words is 24 digits. If we recall to essentially how I opened up this talk, where I sent you first one bit, then 2 bits, then 3 bits, and with increasing complexity, we gained more and more of the error correcting capability of sending digital messages. So the extended binary Golay code, each word has length 24. And it has this property where every single valid code word is a distance 8 apart, which basically means you have to have 8 bit flips in order to go from one valid message to another valid message. Because everything is a distance 8 apart, that means it can correct up to 3 bit flips, right? And this code, it's fairly important because it was used on Voyager 1 when it flew by Jupiter and Saturn, I believe. And the thing about Voyager 1 is that like its memory is very small. So as soon as it takes a picture, it has to like send it off right away. And the error correcting capability of the extended binary Gole code was like super important in being able to obtain legitimate images of these planets. Because if we received a message, an image, and we weren't able to correct the code that defined it, we can't ask Voyager 1 for a resend because it's no longer in Voyager 1's memory. So this code is of fairly good importance. Now, it turns out that the extended binary Gole code, or at least part of it, can form the S5824 system. So codes have what we call weight. Weight is essentially the number of ones in the message. So all of the codes, all of the messages of weight 8 form 5824. So let's first think about some patterns that, as I mention the applications, I will emphasize it again and again. This code has length 24. All of the codes of weight 8 form a Steiner system. This code can fix 3-bit flips. 8 minus 5 is 3. If we have a representation of S5824, which we do, it's the MOG. This MOG tells us that given any 5 elements, what are the other 3 elements that contain these 5 elements? So there is some connection here that, for those interested, might want to look into more. So I'll just note S5824. Okay. The next one is group theory. So I'm in 347 now, so like everything that was taught in 347 is my extent of knowledge, pretty much, of group theory. Now, the thing I want to emphasize in group theory is we had this like massive categorization project, right? The classification of finite simple groups. And within this classification, we found like 4 infinite families of groups that every single finite simple group must belong to, except for like 26 of them. And within these 26 sporadic groups, we have a subset of them which are called the Matthew groups, right? So, actually, I don't really know how to spell it, so that's fine. One of the things about Matthew groups that connects to Steiner systems is M24. So the generators of M24 can also generate S5H24. Details you can read about it. But again, there's the connection 24, 24. So I'll just write this again as 5H24. Yeah, so like basically my whole purpose in like introducing this stuff is just to give a taste of where it's connected to. I unfortunately don't know the like nitty-gritty details. Yes.
What do you mean by generating?
There's a paper that I linked to in my notes. Okay. The next one is sphere packing. Spelled that wrong. Okay, so sphere packing is essentially the question of like how many n spheres can we fit in Rn such that the volume of Rn that is occupied is maximal. And so there's many dimensions in which the problem of sphere packing remains unsolved to this day. However, one of the dimensions in which we do have a solution is, surprise, surprise, 24 dimensions. So it turns out that S5H24 can be used to form what we call Leach's lattice, and Leach's lattice in turn is used to find the optimal sphere packing in 24 dimensions. Pretty cool.
Is that generalizable to other Steiner systems, or is there something special about
There's something very special about S5A24 that makes it applicable to all of these different areas.
What is special about it?
Good question. You can read more about it elsewhere. Okay, and very last thing is something I hear quite often is for every concept that you learn, there is some generalization of it, right? So the idea of Steiner systems is that we required every subset of size t to be in exactly one block. What if we allowed it to be in more blocks? For instance, let's say every subset of size t has to be contained in, let's say, 2 blocks, or 3 or 4 or something. That's a generalization of Steiner systems. And this is part of what's called design theory. So in design theory, they study what are called balanced, incomplete block designs. Okay, abbreviated BIBD. So these balanced incomplete block designs, they have more parameters. Like Steiner systems, it's defined by 3 parameters. BIBDs, there's more things involved. So for instance, if we take a revisit to S123, which we attempted to construct earlier today, it's not possible to require every single element to be contained in exactly one block of size 2, but it is possible to require it to be contained in exactly 2 blocks of size 2. If we have a block, let's say 1, 2, and we have another block, let's say 2, 3, then we could have a third block that's 1, 3, and every single element is therefore contained in exactly 2 blocks. So Steiner systems that don't exist can exist as a BIBD using some amount of blocks, number of blocks. So BIBDs actually have some relevance in experimental design. For instance, let's suppose you wanted to test 3 different brands of eye drop medication. And you could do so by giving one brand, if you fix a participant, and in one eye you drop one of the brands, in the other eye you drop a different brand. So basically, each brand is like your value of t. In this case, t is 1 because 1 brand. But your blocks are size 2 because each person has 2 eyes. So essentially, the question is can you design an experiment such that you can have an equal number of observations for each brand of eye drop? So BIBDs have some utility there. It's also in Stats 305, just fun fact. Okay, so just to essentially recap what we did so far, we essentially talked about the general idea behind a Steiner system. We have a set omega of size n, and we have a collection of blocks where each block has size k,